Hello, this is Professor Kuehn, and welcome back to our discussion of Ptolemy's Almagest. We're looking at Chapter 5 of Book 1 of the Almagest. Again, this is in A Student's Guide to the Great Physics Texts, Chapter 5. In my last lecture, which I suspect you might have found to be a challenging lecture compared to some of my other ones, we were talking about Ptolemy's model of the universe, specifically how he's claiming that the Earth is located exactly at the center of the universe, more specifically, I guess, using his language, at the center of the celestial sphere. So what I've done here is I'm going to first of all remind you of some of the things I was talking about in my last lecture and expand on it a bit. So I have shown here 3 diagrams. Each of these diagrams depicts the Earth at the center of the celestial sphere. So I'm going to put the Earth in green, just color these in as I go. So here's the Earth at the center of the celestial sphere. The horizon in this particular diagram at the top is vertical. That means this is the case of sphera recta, or means the horizon is at a right angle to the equator of the celestial sphere, and this is for the observer on the equator of the Earth. So if you imagine a person standing on this globe, that person is standing right here, they're on the equator, and everything to the right of that brown line is above them, that's visible. Everything below that brown line is invisible, it's below their horizon. And the point that I was trying to make in this is if the sun is riding on this central sphere, remember the outer sphere is the celestial sphere on which the stars are located, the sphere that's concentric with it but a little bit closer in is rotating around once per year. The outer one is rotating around once per year. But as a result of this, the sun is going to appear in front of different stars at different times of the year. Where it's shown right now is the sun appears in front of the stars that are quite low on the celestial sphere. That is the day of the winter solstice, which is about December 21st. Then, as the sun moves around its inner celestial sphere over the course of a year, eventually it will appear in front of these stars. That would be on March 21st. That would be the day of the vernal equinox. Then a bit later, it will appear in front of these stars. That's the summer solstice. That would be on June 21st. And then a bit later, it appears back down here in front of these stars. That would be the autumnal equinox, September 21st. And then finally back in front of the stars down at the bottom where it has a W where it says December 21st. And one of the important points to notice is that as this outer celestial sphere is rotating around once per day, the sun will be above the horizon right there on the winter solstice and below the horizon right here. And likewise on the equinoxes, the sun will be above the horizon for that much time and below the horizon over here. And likewise on the summer solstice, above the horizon right there and below the horizon right here. So notice that there is equal length day and night for someone standing on the equator if the Earth is located at the center of the celestial sphere. Jumping to the next diagram, once again, we have the Earth located at the center, but now we have a case of the horizon is tilted at this angle. Oops, that's kind of, I have a wiggle there. So this is the case of, as Ptolemy would call it, sphera obliqua, which means that the observer is in the northern latitudes. I used the example of Milwaukee. So if we draw the person right here, they're standing maybe up here in Milwaukee. Now the things to the above and to the right would be the things that he could see on the celestial sphere. Above his horizon and down and to the left are the parts of the celestial sphere that would be below his horizon he would be unable to see. Now notice as this the sun, once again, is located here on this internal sphere, so it's rotating around over the course of the year. And notice, once again, this outer sphere is rotating around once per day, and as a result, the sun will appear to be above the horizon on the winter solstice for this much time, and below the horizon on the winter solstice for this much time. So notice that you have long nights and short days on December 21st. On March 21st, the vernal equinox, and likewise on September 21st, the autumnal equinox, the sun is above the horizon for 12 hours, and it is below the horizon for 12 hours. And then on the summer solstice, June 21st, the sun is above the horizon for much longer than it is below the horizon. So that corresponds to long days and short nights. There are 2 days of the year, March 21st, September 21st, on which the sun is above the horizon and below the horizon for equal amounts of time, and that is why, by the way, it's called the equinox, as was named by people who presumably lived in the northern latitudes. Okay. Also, maybe something else I should point out, notice that according to this model where the Earth is at the center of the celestial sphere, the equinox lies midway between the solstices. Okay, now let's talk about the final diagram. In the final diagram, the horizon is at a much, I guess, steeper or shallower angle, depending on how you want to talk about it. The Earth is once again at the center of the celestial sphere, but this is for the case where the observer, this is another case of sphera obliqua, but here the observer is at very high latitudes. In particular, the observer is standing above 67 degrees north latitude. That is in the Arctic or above the Arctic Circle. So that their horizon line is getting closer and closer to being horizontal, okay? And in particular, notice that the horizon line here is actually above the point on the celestial sphere where the sun would have appeared on the winter solstice. This is significant because for this person who's standing at these very high latitudes, way up here, what happens as the sun orbits around on its on the interior on this the smaller circle, so it's going around like this? Well, sometimes during the year, notice that the sun over the course of the day will stay below the horizon for the entire day. That is, it doesn't ever rise above the horizon. That is, there are some times during the year during which the sun is below the horizon for the entire day. So here, all these days. So for this time of the year, the sun never rises during the day. And notice also that on several days of the year, the sun stays above the horizon for the entire day. So anywhere between the dates where the sun is here and the summer solstice, in this period of the year, the sun never sets below the horizon. So if you're standing in the Arctic Circle, there will be one or more days, depending on how high you are above the Arctic Circle, where the sun never sets. It's daytime all day. And that's going to be during the summer months. And then during the winter months, there will be several days around the winter solstice, either one day or more than one day, depending again how far north you are in latitude, that the sun never rises above the horizon. Notice that on the vernal equinox and the autumnal equinox, the sun is above the horizon for 12 hours and below the horizon for 12 hours. Okay? So these are the kinds of predictions that follow from the Earth being at the center of the celestial sphere. Okay, now why are we talking about all this? Because these kinds of predictions do not match what's actually observed if the Earth is off axis. That is, it's farther from let's suppose it's not right along the axis of the celestial sphere. So going back to our first diagram, the top diagram, you might imagine if we had the Earth farther away over to the right, then the horizon, as Ptolemy points out, would not bisect the celestial sphere. That is, you would not have 6 constellations above the horizon and 6 below the horizon. Instead, you might have 4 above the horizon and 4 below the horizon. And that's not what we actually observe in nature. So that's an argument he gives for why the Earth must be on the axis of the celestial sphere. Notice also, if we look at the second diagram, if the Earth was not right on the axis at the center of the celestial sphere, but was located slightly higher up here, then you would have a horizon line tilted like this, and then you would have a situation where the vernal and autumnal equinoxes did not lie midway between the summer and winter solstices. What I ask you to do in the homework is to consider the case where the Earth is either located up or down along the axis, or to the right or left off of the axis.